configuration you need, and then you extend it to add to the list of dependencies, for example. I'm mostly going to talk about dependencies today. Another alternative is you could just say, let's let Zinc handle everything. Let's wait until the tools get smart enough and just deal with cold compiles being very, very, very slow. Stop creating modules. Just go shopping instead. In Pants, this is what a build file looks like. You basically just have to declare that in this directory there is Scala code, and it has these dependencies. Those dependencies, again, 1111. Did I put in an extra one? Anyway, they refer to directories. They also refer to targets. They refer to packages. So there is something called source Scala org pants build zinc options, which is a target. But we're repeating ourselves, right? Because this information that we've put in the build file is stuff that's already in the code. So the idea is that maybe we could do Dep Inference. Maybe we could infer from the sources what the dependencies were supposed to be and put them in the build file. So the imports for a similar target might look like Scala compat Java 8, com, faster, et cetera, et cetera. We're using Jackson. And then we have some internal quote-unquote targets that were just neighbors of the code I was editing, right? And so Dep Inference is really neat because we could extract the imports from, we could extract the dependencies from these imports. We could also extract dependencies from module.java, because we're going to be forced to write one at some point. We all have to figure that out. We could also do other interesting things, like maybe the build system could extract the number of remote processes to run your tests in by looking at your test code. That's actually harder than it sounds, because unless your test runner implements its own facilities for remoting, it can't use the rest of the build's facilities for remote execution there. By the time you get to running the tests, it's too late to decide how many processes are running because you're already running a process somewhere. And so you'd have to use a separate facility for that. So anyway, there's a lot of possibilities here. So the goal is, no file. That file isn't there. That'd be cool. We could just delete all of the build files and drop something like 400,000 lines of code. So consistency. It's really important that if you're going to do Dep Inference, that it's kind of obvious what's happening. So some ground rules are really important. You should only try to do this for really simple import statements. If the import is complex, or it might shadow something, or there's something else that it might shadow, wildcards can be hard. So you want to keep these simple. The upshot, though, is that if you keep your imports simple, you don't have to repeat yourself. Okay, that's a little bit better. A little bit more here, so I don't have to put anything there. And then also, we shouldn't search the entire repository willy-nilly for things that you might have imported. It's good to have some well-known locations where modules might live. And internally we call this science layout, but it's essentially that there is about 40% of Twitter's code organized at the root under source Java and Scala. I say JVM here just because that's how it should be. And then com Twitter package name all the way down. So this is very, very easy to grok, right? Where does this package live in my repository? Well, it lives at this well-known location. So as I said, let's keep it simple. Another option might be that we could add build steps in order to do this. Is this actually a requirement? How you would do this is in whatever tool, add a wrapper script that's going to invoke your build tool, that's going to go out, infer the deps for all of the code, rewrite the files on disk, your build definition, and then invoke the build tool. And this has been done. So I say case study because Foursquare, the Yelp competitor, still an excellent app, about 5 years ago was doing Dep Inference on their Scala code. They are still some of the happiest Scala monorepo developers we've ever seen. It's definitely interesting to talk to some of those folks because they ended up with 2 million lines of code, tons of modules, never really had to edit their build definitions. Kind of great. But it would be nice not to have this be a separate step outside of the build, right? Like, I have to go and rewrite all the files on disk before I can actually invoke my build. And in particular, at Foursquare, one of the downsides was if you made an edit that meant you needed to rewrite a build file, you had to recognize that, because otherwise the build would fail. Like, I added an import. I now need to remember to go and run the build rewriting script. So we want to integrate with the build. Ideally, we could supplement parsing of the build definition. Build definition here is like your build.xml, your build.sc, your build.spt, your build file, depending on which build tool you're using. But build tools don't really make this an extension point. That's challenging. Why isn't it an extension point? Oh boy. Okay, why is it generally not an extension point? Can you do this in any existing tools? And why isn't? Why is it not an extension point, right? It's easy. You're going to recurse and parse more files as you discover files. It's sort of already what happens when you are parsing build files, right? So before we get into that, there are two kind of competing concerns with Dep Inference. Build tools want the ability, they provide the ability to extend themselves, but they also need to provide the ability to introspect what's going to happen or what has happened when a build runs. So we'll get to both of these. First, there's a really important paper that helps describe some of this that I think is currently in a review phase, pre-publish type thing. Build systems are awesome, terrifying, and unloved. Build systems a la carte. And Simon Peyton-Jones is of Haskell fame, but two Microsoft researchers and another British researcher. So this paper talks about mashing up various properties of build systems to create interesting new systems. And so it talks a little bit about storage. It says that the goal of a build system is to bring up to date a store that implements a mapping from keys to values. The keys and the values here, commonly for many build tools, are file names and file content. Make is a very, very simple example. You say that you want some binary file on disk, and in order to do that, it's going to walk the graph of other files that are required, and then build them in a topological order. Mill and Bazel are similar. Mill has JVM names associated with each of these. In SPT and Pants, for example, though, you might actually have like typed polymorphic. Mill is also polymorphic, I believe. But you might have typed and polymorphic keys and values. So you request the test results for some target, which means I can request multiple things for a particular location on the file system, right? Like, give me a REPL for this project, or give me the test results for this project. So BSLC also says that tasks are a way to compute a single output in a side effect free way using a callback to find dependency values. Other systems call them rules, but they're basically the composition units. When you're extending your build tool, you write tasks, you write rules. And these tasks are then executed in some order. So you might execute them topologically, which is basically just doing a topological sort. That requires that you already know what the dependencies of the tasks are, which is important. We're going to get into that. So reordering topological is if I just guess at what the ordering should be, and then as I run tasks, I abort them if they don't have what they need, reorder them, run the things they need, then run them. We call that reordering topological. And it's the one interesting thing about the paper is that they actually claim that Excel is a build tool. I would say that it's an incremental computation engine, maybe not a build tool, but that's fine. But Excel uses that strategy. And recursive. So a recursive ordering is essentially just recursively running tasks as they are required and with some amount of memoization so that you don't re-execute something as you recursively visit it multiple times. The reordering topological is not minimal, because if you abort a task, you might have run half of it, then found out you don't have something it needs. Oh, okay, start over later when I have what I need. Recursive tasks can be minimal if you can suspend them. So you need a good async model, coroutines or monads or etc. Okay, so there's a few components, but what about this decides whether a build system is capable of doing Dep Inference? So there's one more important missing piece that is kind of the core of the paper. So the task that in your build system is generic. Well, sorry. The task that decides how your build system acts is generic on some constraint. If you plug in a functor into your task, you don't get a very interesting build system. And I'll explain why in a second. But it applies a function from a value to a new value. If you plug in an applicative, an applicative is going to, in some context, apply a function from multiple values to a new value. And a monad is going to apply, again, in some context, apply a function from multiple values to a new context. Context, you can replace the word context with wrapper or burrito or etc. What that means in terms of outcomes, though, so if you plug in a functor, you get a series of conversions for a single request. You basically just get a static path, right? No new dependencies can be introduced. You can't have multiple inputs to something. It's a static path. So you can convert one thing through a path. Applicative, you can make multiple requests for dependencies, but none of the requests can be predicated on the outputs of other requests. So you can't look at the output of some request in order to decide whether to make another one. In a monadic system, you can make multiple requests for dependencies, and you can inspect the previous outputs of requests you've made to decide which additional requests to make. And that results in a dynamic graph. Okay, cool. So functor, as I said, not super useful. But with an applicative, you can think of this as, given these known input keys, I'll run this function to compute these known output keys for this known. That should probably be singular, but the output key would be singular. With a monadic system, given some unknown input keys, I'll run this function to compute these known output keys. Okay, cool. This seems like it's an important piece. One more important part of build systems that's important to understand is I've kind of claimed that they have these phases. This is not from the paper, but generally you have a discovery phase at the beginning where the build system is going to go out and find all of the build definition that's relevant to a particular run. So it's going to parse your build files, essentially. Then it's going to run enough task logic to decide what actual processes to execute. And finally, it's going to execute those processes. I separate these because various build systems merge or don't merge various phases. So Bazel, in particular, separates discovery from planning and execution. Mill separates discovery from planning, but merges planning and execution. So coming together, the discovery phase is generally recursive because until you've parsed the build files, while you're parsing the build files, you might encounter a dependency that means you have to go and parse another build file. Okay, that's actually the part that we think we want to extend. Planning is generally once you've already discovered everything that's relevant to the build, and then you're executing user logic. And then execution is also executing user logic. But since monadic builds require recursive execution, it's actually sort of the case that Bazel and Mill are already monadic in that first phase where they're discovering build. Certainly Bazel is. While it's going out and walking build files, and while Pants is as well, it's going to execute in a recursive monadic fashion. But after that, the part that you can extend is topological, i.e. applicative. And Bazel and Mill are both explicitly applicative. But an important point here is most systems are using a mix of recursive and topological. Okay, so let's all be monadic. Monadic, this seems like much, much, much more powerful. So to do Dep Inference, all you have to do is use a monadic extension API, and then during that first phase, cheaply extract the imports from your sources and use that rather than the build file contents. And then The question is really whether you're allowed to extend that phase. It just requires an async model. This seems like it can work. But there's that other half. We need the ability to introspect. We know that this monadic system would allow us to do this, but what would it mean in terms of understanding our build? So for introspection, there are a few really common questions. Why do I depend on this thing? It's super expensive. I don't want to depend on it. Oh darn, I need to because dumb library over there. What do I depend on? What transitively depends on why, which is sort of the what, why, how, who's on first. Anyway, what transitively depends on module y is the CI question, right? Like, what do I need to rebuild when module y has changed? And the user also needs to know what tools and options are relevant to some module that they're building so that they can know what bits to fiddle with. So a friend of introspection is tracing. In either of an applicative or a monadic system, you can record a trace of what executed, and then you can use that for introspection. So you can look at what was required to build what, and you can use it to rebuild incrementally by saying that this file was deep as a leaf in this graph. When this file has changed, transitively invalidate up from that leaf through the graph, leave everything else in the other subgraphs pristine because they weren't affected by this file. I know precisely what was used. So tracing is super useful. In practice, though, you can only use a trace after you've collected it. And so in applicative systems, you can cheaply compute a transitive trace because you don't actually need to execute any of the functions in order to decide. All of the keys are known. The input and output keys are known ahead of time without running any code. Some amount of code, but no user code. And actually, even cooler, you can cache entire subgraphs with minimal execution. So it's called a shallow build. The idea is that if I want to build a Android binary, that is the root of my build. With an applicative system and a distributed build cache, a server that I can go and ask for a particular output for a particular key, an applicative system can walk to the leaves, hash all of the inputs, do one cache lookup to the server, and get that binary really quickly, insanely quickly. And Bazel and Buck both do this. In monadic systems, though, tracing requires a lot more, maybe a lot more, execution. And the paper kind of leaves this as an open question, unfortunately. So you could record traces encoding trees possibilities, and so you could fetch like a tree of possibilities and then use that as your cache lookup. And like encoding a tree that way is basically just minimizing the number of round trips, because otherwise what you do in this system is do a cache lookup for every node in the graph. So maximizing the efficiency of the system is an open question. We think we have some ideas. Okay, so monadic systems are much easier to extend, but much harder to introspect. That's a bummer. So how much introspection can we reintroduce? So I'm going to talk about some of the strategies for reintroducing introspection into monadic systems. So first of all, let's do monads, or monadic rules. It's much easier to implement useful things with monadic systems. And this is me taking a stand. There are plenty of applicative build tools. Shake is a Haskell build tool, and it's one of the build tools cited in the paper as being monadic. Sorry, it is the only build system cited in the paper as being monadic other than Excel. So it's important to notice that the downsides of a monadic system are mostly ameliorated by having a warm graph. So if I have a completely warm graph of some previous run and one thing has changed, there's a lot less work to do overall, right? This constructive trace only is useful if I haven't edited anything. Okay, well, cool. That's for that cold build case. Once you have a warm graph, which we hope is the common case for users, cost to rerun is very minimal, and actually the constructive traces don't get you anything. So we'd like to have monadic rules, we'd like to apply constraints. We'd also like to have polymorphism, right? Rather than just files on disk, we'd like to have types applied to the keys and values of this system. So when you've made a request for some value, you know what its type is, and you know what the type of the output value should be. And in particular, because these monadic systems are so much more flexible, you can expect that you're going to want to build more things with them. And when you build more things, more and more complicated things, you're going to want types to keep you safe. Let's not be stringly typed. And this one is kind of a novel, potentially, strategy for pants in particular. We want to reify the rule graph, and what that means is we want to be able to inspect the graph of rules before running it. So in particular, we can with this rule graph, we can answer the question, for a value of type Scala sources, how do I compute a shaded deploy jar, roughly, right? And I can answer that question abstractly. So even if I haven't seen any of your dependencies, this subgraph encodes all the possibilities for how that might happen, right? We're going to have to invoke a compiler, we're going to have to extract imports, we're going to have to do X, Y, and Z. And in particular, we think this is useful because the larger a system gets, the more, and this is a system in general, as you have a larger system, you stop looking at individual log lines, you know? You start aggregating things across your entire cluster to get a big picture view of what might happen. And then when you really care, you're going to trace one, which we've said we can optimize for, tracing. So, and another question you might be able to answer is, in general, what happens when Scala code depends on C++ code? Like, I can see that there's a path between these. This is a legal thing to do. I know that before I've run anything. So that's useful. Also, we think that one way to avoid the issues that might come up in a monadic system is that you can classify the types, the various types that are in the graph. So really, between an applicative and a monadic system, I mean, a monadic system is just going to run a bunch of user code in order to get you your answer. If that user code has been well-groomed to run quickly, right? If I'm running a Scala native binary to extract inputs, or extract our imports for some Scala sources, that is not significantly slower than parsing a build file. In fact, it might be faster. And so in that case, if you've made guarantees or put bounds on the cost of various types, you can ensure quicker answers for queries that people have commonly, like, what do I depend on? But as I said, it's still possible for a plugin author to get it wrong. If you've kind of like marked something as needing to run quickly and somebody still, you know, says something about creating the universe immediately below your extract imports function, then you might wait a while. So let's tie it all together. This is an example of the rule API that we've come up with in Pants. This is in Python. The rest of Pants is implemented in Rust, and we've slowly been porting more and more to Rust. Rust is excellent as well. The primary language that Pants builds is still Scala, so nothing has changed there. But this is just a simple, the equivalent of a case class. Structural equality, a new type wrapping, an integer. On the bottom, we have an @rule definition. This is an @rule that computes this simple data type, given a single int as input, and running Fibonacci. The yield statements here are interesting. This @rule is a coroutine, meaning that rather than simply returning, it can yield multiple times in its body. this is what allows for this async recursive execution. The Rust code is running through and invoking rules, suspending them when they say that they need inputs, and then resuming them once the inputs have been computed. An interesting thing, though, what else is interesting in here? Right, so this statement here with the x and y on the left-hand side, this is actually going to make a request for n-2 and n-1, the Fibonacci values for n-2 and n-1. When it receives those, it's going to wake back up having received those, and then it's going to yield a final value. Cool, that's straightforward. But another interesting thing is when we defined this code, we ended up with a static rule graph, meaning that without having run this, we have a graph that defines what this rule needs in order to run. And so this little edge on the right-hand side is interesting. Well, we'll talk about the rest first. So if I want to get the Fibonacci value for some int, I'm going to use this rule. And in order to get its first input, it has this parameter n, right? The value you asked for is going to be used as the first parameter there. The arrow on the right-hand side means that it's using itself recursively. So the rule is using itself recursively to compute additional Fibonacci values. And we can also trace it, right? So after having executed a rule, we can see that if we want the 8th Fibonacci value, it will have a value of 21, but we recursively executed and memoized the execution to get there. Cool. Okay, but yes, we're here for Dep Inference. Does anyone have any questions about rules? That's really all there is to it. How we do the static value, how we build a static rule graph is by essentially just parsing the AST of Python code to look for calls to get in the body of an at rule. And we have the constraint that you actually have to mention and or invoke the constructor for the type on the right-hand side. Oh, I'm sorry, question, yes.
Yes, please. Maybe my question will be not so smart. I apologize in advance, but can you please show again this slide with this nice tree of Fibonacci calculation?
Oh, man. Okay, yes.
Yeah, this one,
where
half of the nodes is memoized, right?
Yeah.
You don't calculate Fibonacci of 6 twice, you just reuse the value.
Correct.
What if some of the build steps is malicious or just has a bug and it computes a wrong value and is memoized and later used by some other build steps?
Yeah, that's a good question. So malicious code, one of the things that you can do, one of the things that many of these systems do, is take the execution environment for rules and attempt to make it deterministic, so that there's not much you can do against malicious code, but you can help people not fall into traps around non-determinism or using floating point values in ways that would mean that a rule is non-deterministic. But yeah, all of these systems are kind of assuming trusted user code, frankly. When you install a plugin into your build, yep.
Okay, but even when you trust all your code, some of the steps may have a bug, and that's okay as long as you know where to look for that bug.
Mm-hmm.
And memoizing these computations in this way allows the buggy module to affect some other seemingly unrelated modules, and this would be at least it seems to be really hard to debug when you don't even know what causes the failure.
Well, so buggy modules can affect one another regardless of memoization, but the advantage to having memoized them is I can see where the bug is introduced. So these are the output values of all of these functions. If any of these had thrown an exception, it would kill upward the tasks that also were depending on that task. So if anything, this trace is a really great way to find bugs. If something had been introduced down here, I'd see it as it propagated through the rest of the run. So yeah, It's a hard, this actually helps in that case, I think. Okay, but let's do Dep Inference. This is the rule graph for Dep Inference. It's a little bit larger. There's also probably some noise in here that's less interesting. But at the root, we want to compute a hydrated field, which types TBD, for a Scala sources field. In order to do that, we're going to run a few things. Okay, cool. But let's just dive into one. So if we want to extract the JVM imports from a snapshot is approximately a tar file, tar or zip file. It contains some files rooted at some path. They have relative path names. So I can extract, and in this case, we're assuming, although we needn't, we're assuming that these are Scala files. So shame on me, I should have said select Scala snapshot, right? We have types, let's use them. But regardless, here we're going to execute a process that's going to extract the imports from the files in that snapshot. Executing a process in this system is pretty straightforward. You make a request to execute a process and you get the result. You're suspended while it's running. And then if you get an Xcode you don't like, you can raise an exception, that's fine too. It's pretty straightforward. Once we have a bunch of packages that we need to import, we have this select package address. It's basically given some package, where does it live on the file system? An address in this case is going to be approximately a directory or target or package. If 111 is followed, they're just synonyms, right? But one thing is that it could live in third party. It could be a binary module as opposed to a source module. So there's some ambiguity as to where they live. 111 gets violated, it gets potentially violated in that case if you have a third party module with some package name and you have a source package with that same package name. So the first thing you do is locate candidate directories. You take the package name, use the separator instead of dot, and then collect a series of paths that may contain that package. Once you have those, you request a snapshot for the candidate directories that might contain that package. Then you get you parse the build files for those directories to figure out whether anything exists there. And if you found exactly one, then you're good. You've inferred a dep. Otherwise, if you have ambiguity, then somebody hasn't been following 111 and you can fail. And then up at the top, hydrating the Scala sources. So the first thing we do is get the content of the files, extract the imports from that content, attempt to get addresses for each of the package names that are that are requested or required by those sources, flatten that, and you're done. So it's very decoupled, composable code that runs quite efficiently. So what else is up with Twitter's build team? That's dependency inference. Does anyone have any other questions about this, or any questions about this at all? A lot of code. So a little bit more on status. All of Pants's build file parsing is currently implemented using @roles. And so this is a PR that's out now to add support for Dep Inference for Scala to Pants, using the same system that is used to parse build definition in Pants. So this is monadic in that, although it doesn't look like it, we're not using monadic combinators, we're using coroutines, but the end result is the same. You can use the output of some rule that's run to decide what other rules to run, right? And that might mean using an if statement, it might mean using a loop, it might mean filtering out things that aren't valid, etc. That type of logic is not possible in an applicative system. We needed the monadic features in order to do this. Okay, what else is up with Twitter's build team? Pants did not have a daemon until just this quarter. Took a long time to get in place. We're very excited. But in order to ship that, we ported the backend to Rust, created a new engine that I'm demonstrating here. We also switched Pants from Ivy to Coursier, so thank you, Alex. It's significantly faster and much less synchronous, so huzzah. We're going to continue polishing the at-rule-based engine. We're also working on remote execution. What that means is taking this graph and executing it on a cluster. Because we're a monadic system, we're not sprinting through, collecting the entire thing, and then attempting to run it topologically. But as we expand the graph, we'll immediately fire off the processes involved in executing it on the cluster. We're also investing in C and C++ support, and we're hiring. We're already a distributed team. So I mean that concretely for the first time in a while. The build team is hiring. So we're looking for excellent folks, and I expect there are some here. So I'd love to talk to you. Thank you. And does anyone have questions? Got questions?
Hey, quick question. So how does this dependency inference play with IDE support?
It's a good question. So IDE support. Pants has IDE integration for IntelliJ currently, and we have a plugin. So because we have a plugin, IntelliJ is periodically calling the Pants export goal, which is exporting Pants's view of the build graph to the IDE. And so it just works. Really, from the perspective of someone outside Pants, the rest of this presentation is kind of a long-winded way to say, like, here's how you provide extensibility for the phase of a build tool that usually does the build file parsing. If you have actual extensibility for that phase, it's completely transparent that how you are collecting the dependencies. And so it doesn't end up affecting consumers of the tool at all.
So it sounds like most build tools really want to try to understand the task graph. They have some mechanism to reify the task graph using applicatives or something to understand what's going on. And it seems that, well, there are multiple reasons. One of the big reasons is introspection, right? Or predicting ahead of time that the outcome isn't bad. Now, I mean, software is complex in general. Not just build tools are complex, other softwares as well. And we always want introspection capabilities to help us. And there are things like type systems that are ahead of time static analysis. There's stack traces at runtime that give us, or runtime debuggers. It seems like some build tools give the impression that build tools are somehow a special case that need more or specialized capabilities there. Do you have an opinion about this? Or is it based on the languages they use that they need more capabilities than the languages they are currently using, but other languages could offer that?
Yes. So I think build tools are a heavy user of incremental computation. There are other use cases for incremental computation and incremental and adaptive computation. While reading this paper, I was surprised to see one of my Twitter colleagues who started on the same day as I did 7 years ago cited for an adaptive computation paper, so I need to go and talk with him about that. But adaptive and incremental computation are definitely used in other places. I think the ability to introspect is a bit of a deciding factor, because in many cases, when you are writing a general system that uses incremental or adaptive computation, your primary concern is overhead. So you just want to run as quickly as you possibly can. And so in the context of other, like there's a Rust incremental computation engine called Adapton, and the only thing they ever tout is how much overhead they have over non-incremental computation, right? We focus a little bit less on that. We probably should focus more on that. But yeah, introspection, I think, is the thing. it's totally true that in production you'd want to be able to introspect your system, but you probably don't want to pay a whole lot for it. So it's a challenge. Any other questions? Okay. Thank you very much.